Dr. Saurav Chakrabarti, working as an associate professor in the computer science group at the Chennai Mathematical Institute, Tamil Nadu. Before joining Chennai Mathematical Institute, he was a postdoctorate at the Algorithms and Complexity Department of CWI, Amsterdam, Netherlands. He was a postdoctorate at the Computer Science Department of Technion, Israel. He was awarded PhD in Computer Science from University of Chicago. His area of research is theoretical computer science. His focus has been in the classical and quantum complexity of Boolean functions, including property testing, sensitivity, block sensitivity of Boolean functions, and quantum database search in electronic commerce, in graph algorithms, and in coding theory. He has published several research papers in both national and international journals.
Welcome to the UGC lecture series in computer science, and the topic is algorithms. So, today we will be looking at minimum spanning tree, and we will be looking at one particular algorithm for finding it, Kruskal's algorithm. So, till now we have been looking at various applications of graphs and how to look at various algorithms of graph. So, today is also one of those days, but let us start with a real life problem. Say in India, an internet provider company wants to lay some special fiber optics cable all across India in such a way that they want to make sure that any city is connected to any other city. So, at least if somebody from one city wants to call another city via internet, it should be very fast. So, any city to another city must have a connection via the better cable line, and of course, the internet provider wants to optimize its own profit. So, it wants to minimize its cost. Now, clearly the cost happens because of the amount of cable laid. The cable is the hard work. So, it wants to minimize the length of the cable laid. So, this is the problem. You can imagine that such kind of problems occur in almost a day to day basis all across the whole planet till right now. So, how do you solve such a problem? So, as I told you earlier, almost all of these problems or many of these problems can be formulated in graphs. So, let us start with the graphs. So, again just to describe, so we have to define some n vertices and some pairs of edges E1 to Em. Now, graphs are some mathematically interesting objects. They help in expressing relationship between objects. They are very simple and very general. Many real life problems can be modeled in this wording of graph theory. And so, if we have a better understanding of the structure of graphs or algorithms for graphs, then we are in a good shape. So, for example, in our setting, say we have these cities. We represent these cities as vertices. So, I have just labeled the cities as A, B, C, D, E, F, G. So, these cities you can think of vertices. Now, they have just been put up somewhere. Now, between cities there are roads, but you can clearly see that the roads have been drawn and they also represent vertices, edges. So, already we have transformed our kind of input to an undirected graph, and again between two cities there are some distances. So, for example, distance between A to B is 7, distance between A to D is 5, maybe the distance between A to F is either you go from D or you go from B and E, there is no other way of going from A to F directly. So, now this is our original problem instance. We have been given the set of cities, the roads and the distances between them. Now, what do we want to find? So, what do we want? We want to lay cables. Of course, when you lay cables, we have to connect these cities. In other words, we have to select some edges such that all the cities are connected to each other, meaning between any two vertices there must be a path, some path. Right now, we do not care whether it is the shortest path or longest path or something. There must be a path, at least they should be connected, and we should minimize the length of the total cable laid, or in other words, the sum of the weights of all the edges means sum of the total cable laid should be minimized. So, here we are. So, we want to select some set of edges, so that the graph is connected. This is what is called a connected graph, correct? Between any two vertex, if there is a path from u to v, then we call that graph connected. So, we want to basically find a connected subgraph of minimum weight. So, this is where we have to come to this, but something similar, a notion of called trees. So, a connected graph G on n vertices is called a tree if the first definition itself tells us what we are looking for. G is minimal. In other words, you cannot remove any other edge from it. If you remove an edge, then the graph will get disconnected. There is a similar notion or similar definition or equivalent definition, which is that G has no cycles. So, let us try to understand why are these two definitions similar or equivalent. So, if I have a graph G on n vertices that has no, that is say minimal, then why can't it have a cycle? The idea is simple. So, here is a graph say, and in this graph somehow there is a cycle. Now, it is connected, meaning from any vertex I can come, I can walk to any vertex. But what happens if I remove one of these edges? Of course, I know that if there exists a path that kind of uses this edge to go, say maybe there is a path from here to here that uses this, that earlier was using this edge to go from this point to this point, it can now go along this a path, come here, then go along the rest of the cycle and then come here. So, if it is minimal, then it cannot have a cycle, because if it has a cycle, I can remove one edge or any edge from that cycle and still ensure that the graph is connected. So, minimality and cycle are same. There is another definition which has that G has n minus 1 edges. I will not exactly go into why it is true, I will let you guys go back and think about it. It is a very simple argument. It is one of the most basic arguments in discrete mathematics to prove that a graph that is minimal and has no cycle or has no cycle and is connected has n minus 1 edges. So, in other words, let us think about it. What we were looking for? We were given a graph, we want to look at a subgraph that is connected and has least amount of total edge weights. If it has the least amount of total edge weights, now if there exists a edge that I can remove and still keep the graph connected, then why would I keep that edge? That does not help. So, in other words, I am looking for a tree, a subgraph that is a tree. So, this is called a spanning tree. Given a graph G, a spanning tree of the graph G is a tree that touches all the vertices of G. So, is basically it is the minimal connected subgraph of G, means you cannot remove any more edges. Now, we want to minimize the cost of laying cables. Note that here we have been given not just a graph, but a weighted graph. So, what we want to find out is what is known as a minimum spanning tree, in short it is called the MST, and that means it is the tree with the minimum total cost of weights of the edges. So, if you look at the tree and the weights associated to all the edges in the tree, note that the tree has n minus 1 edges. So, total weights on all those n minus 1 edges, then I will get a minimum cost. Say for example, here I have this graph and have a weighted undirected graph, and I want to look at the spanning trees of this graph. A graph can have many spanning trees. Note the spanning tree is just a subgraph, that is a tree, meaning it does not have a cycle and it touches all the vertices. Here is the graph. One thing to note is that why is this a spanning tree? First of all, it is spanning tree because all the vertices are touched, so it is connected, and secondly it is a tree because either we can see it that they do not have any cycle, or we can also see that if I remove any one of the edges, some vertex will be left out, or the other one is that here the total number of vertices is 7 and the total number of edges that I have colored red 1, 2, 3, 4, 5, 6 n minus 1. So, it clearly shows that the set of edges colored red forms a spanning tree. Now, what is the weight of the spanning tree? It is the weight is the sum of all the edge weights, and here it comes to 54. Now, there can be some other spanning trees also. For example, this is a spanning tree. Again, note that all the vertices are touched, total number of edges is again just 6, mean it is a spanning tree, and if you sum it up, the edge weights is 45. Similarly, here they have another spanning tree, the edge weight is 39. In other words, a graph can have many spanning trees. We have encountered spanning trees in past, where we have encountered spanning tree in our BFS and DFS algorithms. In the breadth first search and depth first search algorithm, we had actually generated a spanning tree of the graph, but there we were looking at unweighted graphs. So, we were just interested in getting one spanning tree and possibly looking at under some other properties about whether there is a cycle and whether there is an even cycle and so on. Here we are not interested in these cycles and so on, but here we are interested in finding the minimum spanning tree. So, in other words, the problem boils down to given a graph G and its weights, I want to find the minimum spanning tree. So, let us try to come up with an algorithm of it. To get an algorithm, we have seen a few different kinds of algorithms. We have seen divide and conquer algorithm, that we have seen how we can divide it into sub problems, so that the sub problems are easy and combining them is easy. We have also seen the dynamic programming algorithm that we saw in the last few lectures, where you divide it into sub problems, and the sub problems you solve them recursively, store the data in somewhere in a nice way, and then combine this data to get the actual problem. In this lecture, we will see a new one called a greedy algorithm. So, as it suggests, greedy algorithm is basically nothing but greedily solves the problem and proves that the output is right. These algorithms are easy to write or easy to guess what the algorithm is, but it is slightly hard to prove that the algorithm outputs the right answer. So, we will take a short break now. After the break, we will come back and see the greedy algorithm for finding the minimum cost spanning tree. Welcome back after the break. Before the break, we were looking at how to find a minimum cost spanning tree, and we told that we will solve it using a greedy algorithm. So, here is the idea of the greedy algorithm. The idea is that first pick the minimum weight edge, then pick the next minimum weight edge if possible. What do we mean if possible? See, the notice that we do not want to get a cycle. If we get a cycle, then we will not get a tree. So, we pick an edge as long as a cycle is not formed, and then you come up with another one, which is pick the next one, and if it does not again introduces a cycle, pick that one and keep on doing it. It is clearly greedy because we are not doing anything non-trivial, and it is not clear at all by looking at this slide that or this idea of the algorithm that the algorithm will ever give a right answer. That is what the problem with the greedy algorithms are always. For example, here say I look at this algorithm, this is called the Kruskal's algorithm. So, first pick up the smallest weight edge. The smallest weight edge is AD. So, we pick that up. Now, once we pick that up, we will color the two endpoints of this edge with a color red. Now, pick the next one. In the next one, say the next one is this edge EC. So, we again pick that one, and now again we color them with a color, but a different color than what we colored AD. The reason is that we want to keep a tab on which nodes occur in which connected components. So, let us pick the next one, and the next one is, as you can see, it is a DF, and we pick DF, and DF does not cause any problem because it does not create a cycle, and more importantly I color F the same color as D. So, if I pick an edge such that neither of these two edge endpoints are colored, then I color them with a new different color. If one of the edge points is colored with something, I will color it in that with that color. Let us take the next one. The next one is say AB, and I pick AB, again I color B with the color A. Now, what is the next one? The next one is BE. Note again that this edge is touching one red color with one green color. So, what does this red color and green color signify? This all the red color vertices are in a single connected component. So, importantly, if I want to pick the edge BD, this edge say, I should not be allowed to do because they are in the same connected component, and since they are same connected component, so I know that there must be an edge from B to D, a path from B to D. So, I will be introducing a cycle, which is not what I want. But if I am looking at this edge say, then what happens is that one edge is in red and another one is in green. So, I will not be introducing cycle. So, this red colored and green colored are trying to understand what are the connected components of this graph till now as we have chosen, and by looking at whether an edge is both the vertices are same color or not will tell us whether I am introducing a cycle or not. So, now say here I take this edge BE. Now, when I take this edge BE, as I told, one of the vertices is red, one of the vertices is green. So, I am not going to introduce a new cycle. Then this E will be in the same connected component of B. So, I need to color E with red, and everything here will red. So, in other words, I will color this one as red. Usually how it is done is that people wants to keep one to store the colors, one tends to keep a member or some leader of that connected component. So, I just use colors here, but usually when it comes to writing an algorithm, people tend to use one of the member vertices as the leader of the connected component, and that helps to understand the color. Now, once we come here, what is the next one that we have? The next one says EF, EF is 8, but EF is something we cannot choose because they both of them are of the same color. I mean, it clearly shows that if EF is chosen, since it is in the same color, I have anyway a path from F to E, and then I will get a edge. So, I will get cycle, which is something I do not want. Next one is BC, which again we cannot choose because they have the same color, and I would have get a cycle. Then BD, again we cannot choose because they have same color and they will get a cycle, and then we choose EF, EG, at least this one was not even colored. So, I can color them, and I keep on doing it till we get our tree. Now, that we have got our tree, one thing to say is that, I mean, did this tree come out of magic, or is it like the choice of example was wrong and that is why it ended up giving a tree. So, such questions can naturally be asked because it is a greedy algorithm. I did not actually ensure anything here. So, a pseudocode of this Kruskal's algorithm is kind of clear. For every vertex you maintain a color, or this is called the set or set of vertices that are connected to V, and you pick an edge u v. If the two sets are different, then you select this edge and you change the color of these vertices, or S u and S v are changed. Now, this is fine, pseudocode is okay. We have an algorithm, it looks like an heuristic algorithm. The pseudocode is also not hard, but what is hard is the correctness of the algorithm. is the output graph connected? Is the output graph a tree or is there a cycle? And more importantly, is it a minimum cost spanning tree? So, let us see how to check whether the output graph is connected. The idea is simple. Here is say the main graph, and let us look at the set of edges that I have chosen. That means, if it is not connected, so there is this set of edges, set of vertices that has been say chosen and colored red, and there is some vertex here that are not colored red. But since this graph was connected to start with, so there must have been an edge from here to here. Now, consider the first edge that goes out of this vertex, this connected place. Now, when I came to the point of this edge being chosen, I knew that this vertex is colored red and this vertex is not colored red. So, in that case I would have chosen this path, this edge. In that case, this one must also be inside this color, which was not. So, this gives us a contradiction. So, in other words, if the original graph was connected, then this graph, this T is also connected. At the end, all of these vertices must end up in the same set. If they do not, as I just showed you, there must be some problem. At some point of time, I must have chosen one edge. This is a typical way of proving a greedy algorithm by contradiction. Let us look at the next one. Why there is no cycle? This is kind of easy slightly, as I had explained while doing the algorithm, that since I have never picked up two vertex of the same color or same set, so there cannot be a cycle, because say at the end I have this graph I have chosen finally and I get a cycle. So, this is my output of the say Kruskal's algorithm, and there is a cycle like this. Now, this cycle happened, then what was the last time one of these edges of the cycle chosen? Let us without loss of generality assume that this was the edge that was chosen at the very last. But when it was chosen, then all of these vertices must have been the same color, because all of them were chosen already, and therefore, all of them are in the same connected component, and so these all of them must have colored red. In that case, how did I choose this edge? That cannot be. So, whatever the output is must be a cycle free. So, at least these two things ensures that the Kruskal's algorithm outputs a tree. The next question is that, is this a minimum cost spanning tree? To prove it, again we have to go by contradiction. But before that, we have to understand some properties of trees, that is very essential. In a tree, the idea is that if I add any edge, then I should get a cycle, and if I remove any other edge from that cycle, then I will get a tree back. They are the two properties that are very crucial. The third property is that, so there is a unique path between any two vertex in the tree. So, using this one, I will try to prove that Kruskal's algorithm does output a minimum spanning tree. So, let T be the output of the Kruskal's algorithm, but let T min be an MST. So, T min is some minimum spanning tree. So, therefore, let us order the edges in T min according to weights. Consider the first edge u v or smallest edge that is in T min, but not in T, or the first place where it changes. Let E be the kth smallest edge in T min. Note that, so let us also be the E naught be the kth edge of T. So, kth edge is like the at the kth edge the algorithm has picked up an edge and that was a mistake. Can that be a mistake? That is the question. So, it is a mistake. If that is a mistake, whatever happens, it means that the weight of u naught v naught must be less than or equal to weight of u v, because at this stage, since E was the first smallest stage that is in T min and not in T, then at this stage, when rather in the k stage, when we are looking at u naught v naught, if weight of u v was less than u naught v naught, then Kruskal's algorithm would have picked up u v. It would not have created a problem or a cycle, because in the tree T mean there is no cycle. Tree mean had same set of edges till the I have picked up this edge u v. So, the weight of u naught v naught must be less than or equal to weight of u v. So, what do? We will try to show that there exists some other minimum spanning tree such that this tree matches in not just the first k minus 1 edges, but in k edges, meaning a tree there is another MST where it matches with our output in the k minus 1 as well as the kth edge. Basically, we can prove it by saying that this is our T. Now, this is an edge say that is not in the T, but in T naught. I will add this edge, and by adding this edge I will create a cycle, and I remove the smallest edge from this cycle, and by doing so I will ensure that I get an MST that is smallest or tree that is weak lesser weight than T mean. So, if this is a T mean and this is the edge u naught v naught, I add u naught v naught, I get this cycle, at least one of them must have a lower edge weight, higher edge weight than u naught v naught. I will remove that one and we will get that. So, this way we can ensure that whatever Kruskal's algorithm outputs is correct. What is the runtime of this algorithm? The main step required is to sort all the edges, which we have seen the sorting algorithm takes e log e steps, the rest of them takes order e steps. So, total runtime is order e log e. To summarize Kruskal's algorithm, we can output the minimum spanning tree of a graph in order e log e steps. Question is that can we do better? We will come to that in the next lecture. So, that brings us to the end of this lecture. So, we have seen minimum spanning tree and how to find it using a greedy Kruskal's algorithm. Thank you.